Imagine you've got two Lego models, right? And they're made from the exact same set of bricks. The parts list is identical. But when you build them, you end up with two completely different structures. Well, that's kind of the puzzle we're diving into today in the world of chemistry. How can molecules with the same exact formula be entirely different things?
So how is that even possible? It's like you bake two cakes with the exact same ingredients, but one comes out all light and fluffy, and the other is basically a brick. This isn't just a weird accident, it's a super important concept in chemistry, and we're about to figure out the secret.
All right, let's meet our two molecular cakes, maleic acid and fumaric acid. Now look at their chemical formula. It's identical, C4H4O4. That means they both have exactly 4 carbons, 4 hydrogens, and 4 oxygens. On paper, you'd think they're perfect twins.
But if they're really twins, they should behave the same, shouldn't they? Let's put that to the test. We'll start with maleic acid. Its melting point is 135 degrees Celsius. Okay, seems pretty normal. Now, what about its so-called identical twin?
Whoa, fumaric acid doesn't melt until it hits a staggering 287 degrees Celsius. That is more than double the temperature. So they have the exact same parts, but they are clearly, fundamentally different substances. What is going on here?
So the first clue to cracking this mystery is realizing that the chemical formulas we draw on a flat screen don't tell the whole story. To get to the real answer, we've got to stop thinking in 2D and start thinking in 3D.
And that brings us to this key idea, stereoisomers. It sounds like a complicated word, but it just means molecules that have the same formula, the same atoms are connected to each other, but they have a different 3D arrangement in space. The key isn't what the atoms are connected to, but where they're actually sitting.
But what locks these different 3D shapes into place? I mean, why don't the atoms just, spin around and change things up? Well, the answer is in the chemical bonds that hold the whole thing together. If you have a single carbon-carbon bond, it's pretty flexible. Think of it like an axle connecting two wheels. Those wheels can just spin and spin freely around the axle, and nothing's going to break. It's a dynamic connection.
But a double bond? Oh, that's a whole different story. It's rigid. It's like taking those two axles and welding them together. Now those wheels are totally locked in place. There's no more free rotation. You can't just twist it.
And this right here is the heart of it. Because of that rigid, untwistable double bond, one 3D arrangement can't just spin around and morph into the other one. It's stuck. And that's what creates a stable, separate molecule with its own identity and its own unique properties.
Okay, so does this mean that every single molecule with a double bond has a 3D twin? Well, not quite. It turns out there are two very specific rules a molecule has to follow to have these things called geometric isomers.
Here they are, the two golden rules. First, you absolutely need that restricted rotation we talked about, like a rigid double bond. And second, this part is crucial, each of the two carbons in that bond has to be attached to two different groups. Let's see these rules in action. Okay, let's take a look at a molecule called propene. It's got a double bond, so rule 1 is a check. But if you look at one of the carbons in that bond, you see it's attached to 2 hydrogen atoms. They're identical. That fails rule number 2. So, sorry propene, no 3D twin for you.
Now let's try butene. It's got a double bond, so check. And what about the carbons in that bond? Well, each one is attached to 2 different things, 1 hydrogen atom and 1 methyl group. It passes both rules. So yes, butene does have a geometric isomer. It's got a 3D twin out there.
So we know these molecular twins exist. Great, but how do we tell them apart? Well, chemists use 2 really simple labels that just describe their shape, cis and trans.
It's actually really straightforward. Cis is just Latin for on the same side. So in a cis isomer, the bigger, similar groups are hanging out on the same side of that double bond. And trans is Latin for across. In a trans isomer, those same groups are on opposite, kind of diagonal sides of the bond.
And with that little bit of info, we can finally solve our original mystery. Maleic acid, the one with the low melting point, is the cis isomer. Its bulky groups are all crowded together on one side. And fumaric acid, our high melting point champion, is the trans isomer, with its groups arranged neatly on opposite sides.
This simple flip in shape from cis to trans creates this huge cascade of effects on the molecule's properties. Just like we saw, the trans isomer has a way higher melting point and it's generally more stable. But look at this, the cis isomer is usually more polar and, get this, it often has a higher boiling point. So what's up with that?
It all comes back to shape.
The straighter trans isomers can pack together really neatly into a solid crystal, almost like a perfectly stacked wall of bricks. It takes a ton of heat energy to break that strong structure apart. The bent cis isomers, though, they're kind of awkward. They can't pack tightly, so they melt way more easily. And the boiling point? That comes from polarity. The bent cis shape often creates a little electrical charge, making the molecules kind of sticky in liquid form, so it takes more energy to pull those sticky molecules apart and turn them into a gas.
So there you have it. The massive difference between maleic and fumaric acid isn't some kind of chemical magic. It's a direct result of that rigid double bond, which locks the atoms into two different, stable 3D shapes. One little twist in space creates two totally distinct molecules from the exact same list of parts.
The big takeaway here is that in chemistry, shape is everything. And this one simple example just blows the door open to a much bigger question. If a tiny change in 3D structure can so drastically change a molecule, what other invisible architectures are defining the world all around us, from our medicines to our food? What else are we missing when we only look at things on a flat surface?